Hello and welcome to another one of D's ADD videos. Today we're going to be discussing more complex examples of drawing Lewis structures. Okay, so these are the rules. You should know them by now. We've gone over them a few times. Count the valence numbers, sum them up, draw the skeleton structure, draw in your bonding electrons and lone pair electrons, and try to make it octet. So the first example I'm going to give you is one in which all the formal charges don't equal zero. All the ones we've done so far, the FCs have equaled zero and it's been neutral. Let's look at carbon monoxide. Carbon monoxide is very dangerous and very toxic, and it ends up destroying our ability to carry oxygen by attacking hemoglobin. But that's not chemistry. Chemistry tells us that this has 4 electrons, this has 6 electrons, so we have a total of 10 electrons. Then we draw the skeleton structure, try to make octets without random lines going through your screen. So we try a single bond, and that would be 2, 4, 6, 8, 10, 12. That's too many electrons. So we're going to try a double bond. And we notice we have 2 and then 4 to get the octet there. And, oops, no. So 4, and then this would be 2 and 4, so that's 2, 4, 6, 8, 10, 12. Still too many, right? Whoa. Let's go back over here. So let's try adding a triple bond, and hopefully it'll match up when we do a triple bond. So if I do a triple bond, I have -6 bonding electrons, and that leaves 4 lone pair electrons. And once you know it, this guy is 2 away from having a complete octet. And this girl, so you guys don't think I'm sexist, is 2 electrons as well away from completing their octet. So that right there, my friends, would be a valid structure as far as electrons are concerned. What do we have to do now? Those of you that said calculate the formal charges are correct. So the formal charge for carbon is going to be 4 minus 3 bonds plus 2 lone pair electrons. Uh-oh, look at that, we got a -1 charge. So what should the oxygen charge be for this to be valid? It should be +1, right? Because the net charge of this carbon monoxide was 0. So here, let's see if that's indeed true. We got 6 valence number -5. Oops. -3 bonds plus 2 lone pair electrons equals a +1. Alright? So the net charge of these two gives me a 0 charge as we wanted. So yeah, that's going to be a valid Lewis structure right there. Even though it has 2 formal charges, all the other ones didn't even match up in electrons. And that's a fundamental part of it. Alright, let's look at one that violates the octet rule. Let's look at phosphorus pentachloride. And if we were to look at phosphorus, phosphorus is in the fifth column, and chlorine's a halogen, so we got 40 electrons to work with. So if I draw the skeleton structure, phosphorus would have to be central, and we would have to have chlorines around the phosphorus, some sort of array. And if I were to look at the periodic table, phosphorus is on the third row, or third period, and because the central atom is on the third period, we can use the expanded octet. Okay, keep that in mind. So I would need an expanded octet because I need to at least form a single bond with all of these chlorines out here, right? So that would be 10 electrons, which is 2 more than the 8 for the octet. Let's see if that works out nicely. These are bonding electrons. So that gives me 30 lone pair electrons. It's a lot, but each one of these chlorines are going to get how many? 6, right? And how many chlorines are there? There's 5 of them. So 6 times 5 gives me the 30 lone pair electrons I wanted. So this one wasn't as bad as you thought it might have been. Don't forget, third period or below allows for expanded octet. So third period or below. This is due to the addition of the D subshell. Okay. Finally, I'm going to look at an ion. Let's look at NH4 plus. Yeah. So here we have nitrogen. Nitrogen is in the fifth column. I'm tired. I was going to say the fourth. Whoa. So we have 5 plus 4 hydrogens times its valence equals 1. And this is for a cation. So that's going to give me a total of 9 electrons to work with. But I notice that there's a plus sign there, so the plus sign takes away an electron. We lost an electron. So now we have 8. Nitrogen would have to be the central atom. If I form a single bond with each of the nitrogens, there's not much else I can do because I have already used up all 8 of my electrons, right? But the key right here was that anytime we have a cation, subtract the charge from there. So this was because it was a +1. Had this been a +2 charge there, then this number would have been a +2 electrons, or -2 electrons, sorry. And then let's do our formal charges just to make sure. So 5 minus 4 plus 0 equals a +1 charge. Okay, so the net charge is a +1. That's good. Had it been something besides a +1, then you know your structure is probably not valid. Alright, let's do an anion. We're going to do IF4 minus. Alright, so here we have 5 halogens, so 5 times 7 is 35 electrons. But we have what? We have this minus sign. That minus sign says that we have an extra electron. So what do? We add 1e. To get 36 electrons. Where did that extra electron come from? Right here. It came from this minus charge. Right there. Okay? So now, business as usual. Let's draw the skeleton structure between iodine and fluorine. Fluorine is more electronegative, and also because of symmetry, we would have iodine in the middle. Oops, not all. Yellow's a little too bright for actual structure work. Let's go back to red. And then we have 4 fluorines. I form a single bond with each of these fluorines. Then I have... Remember, halogens tend to only form one bond, and the rest go as lone pairs around them. Alright, so I had 2, 4, 6, 8 minus 8 bonding electrons gives me 28 lone pair electrons. Now, here I have 6 times 4 is 24 lone pair electrons. So I've got 4 left over. Well, I know that they're not going to go on the fluorines, and I can't form additional bonds on the fluorines, so what I must do is I must surround the central atom with those extra ones. Okay? Now let's see if our charges make sense. Here we're going to have the formal charge for the iodine would be 7 minus, we got 4 bonds plus 4 lone pair electrons gives me a +1 charge, right? Right, indeed. And then the formal charge for fluorine would be 7 minus oops, I just realized I can't subtract. This is what happens when you wake up at 5 a.m. and start making videos. 7 minus 8 is -1, not a +1. And here we have, let's see, what do we got going on here? Fluorine has 1 bond, each of the fluorines, right? And 6 lone pair electrons. Now I don't have to do 4 formal charge calculations because each of these fluorines have the same pattern of 1 bond and 6 lone pair electrons. So we did get the net charge that we wanted, so we would put a -1 out there, and we could put a minus charge right there if you wanted to. Alright, so those are some of the more complex examples. Please practice these as much as you can, because next we're going to go into hybridization, and if you don't understand this, you will be in trouble. So I'm forewarning you now. Thank you, and have a nice day.